In 1969, a mathematician named Volker Strassen discovered something that should not have been possible. He found a shortcut, a way to multiply matrices using fewer steps than anyone thought was the minimum. For 56 years, nobody could do better. Then, in 2025, an AI did. Every time you ask ChatGPT a question, every time an AI generates an image, every time a self-driving car recognizes a stop sign, the same operation happens trillions of times. Matrix multiplication. Here is how you learn to multiply two matrices in school. You take each row of the first matrix, each column of the second, and you multiply the entries together one by one. For 2 by 2 matrices, that is 8 multiplications. Now scale that up. A single layer inside GPT-4 multiplies matrices with thousands of rows and columns. A single response might trigger millions of these operations. Across all of Google's data centers, matrix multiplication consumes a measurable fraction of the world's electricity. So here is the question. What is the fewest number of multiplications you actually need? In 1969, Volker Strassen asked a seemingly absurd question. Can you multiply 2 by 2 matrices with fewer than 8 multiplications? The answer, against all intuition, was yes. Strassen defined 7 intermediate products. M1 equals the sum A plus D times the sum E plus H. M2 equals the sum C plus D times E. M3 equals A times the difference F minus H. M4 equals D times the difference G minus E. M5 equals the sum A plus B times H. M6 equals the difference C minus A times the sum E plus F. M7 equals the difference B minus D times the sum G plus H. Now here is the magic. From these 7 products, you can reconstruct all 4 entries of the result matrix. The top left entry equals M1 plus M4 minus M5 plus M7. The top right equals M3 plus M5. The bottom left equals M2 plus M4. And the bottom right equals M1 minus M2 plus M3 plus M6. Count the multiplications. 7, not 8. We traded 1 multiplication for several extra additions. But additions are cheap. Multiplications are expensive, and that single saved multiplication changes everything. Look at M1 again, the quantity A plus D times E plus H. This single product contributes to both diagonal entries of the result. Strassen found combinations that do double duty, covering multiple output entries with a single multiplication. Winograd later proved that 7 is optimal. You cannot multiply 2 by 2 matrices with fewer than 7 multiplications. Strassen did not just find a shortcut. He found the best possible shortcut. Here is where Strassen's trick becomes powerful. Take a 4 by 4 matrix and divide it into 4 2 by 2 blocks. Now treat each block as a single element. Multiplying the 2-block matrices requires 7 block multiplications by Strassen's method. But each block multiplication is itself a 2 by 2 matrix multiplication. Apply Strassen again. 7 times 7 gives 49 scalar multiplications for a 4 by 4 matrix, down from the schoolbook's 64. You can see this as a recursion tree. At the top level, 7 branches. Each branch spawns 7 more. The total number of multiplications grows as 7 to the power of the recursion depth, instead of 8 to the power of the depth. That difference between 7 and 8 is why the asymptotic complexity drops from n cubed to approximately n to the 2.807. For the specific case of 4 by 4 matrices, this gives exactly 49 multiplications. And for 56 years, 49 was the best anyone could do. To understand how an AI could improve on Strassen, we need to see matrix multiplication in a completely different way. Not as an algorithm, but as a mathematical object. Consider all the information needed to define 2 by 2 matrix multiplication. For each entry of the result, you need a rule that says which pairs of inputs to multiply and add. You can encode all of these rules in a single 3-dimensional array of zeros and ones. This is the matrix multiplication tensor, T222. Think of it as a cube, 4 units on each axis. Most entries are 0. The ones that equal 1 mark exactly which input pairs contribute to which output entry. This tensor completely defines what matrix multiplication means for 2 by 2 matrices. Now here is the connection to fast algorithms. Every matrix multiplication algorithm corresponds to decomposing this tensor into a sum of simple pieces. Each piece is a rank 1 tensor, which is just the outer product of 3 vectors, and each rank 1 piece corresponds to exactly 1 scalar multiplication in the algorithm. Strassen's algorithm decomposes T222 into 7 rank 1 pieces. The schoolbook algorithm decomposes it into 8. Finding a faster algorithm means finding a decomposition with fewer pieces. This is the tensor rank of matrix multiplication. DeepMind turned this into a game. Start with the full tensor. At each step, choose a rank 1 tensor and subtract it. Your goal? Reduce the entire tensor to 0 in as few steps as possible. They called it the tensor game. The search space is enormous. At each step, you must choose 3 vectors. For the settings DeepMind considered, the number of possible moves at each step exceeds 10 to the 33rd power. That is 30 orders of magnitude larger than the game of Go. In October 2022, DeepMind took the first crack at this with AlphaTensor. They built an AlphaZero style system, the same architecture that had conquered chess and Go, and pointed it at the tensor game. The results were remarkable. For 4x4 matrices over a special number system called F2, where 1 plus 1 equals 0, AlphaTensor found a decomposition using only 47 rank 1 pieces. That is 2 fewer than Strassen. But there was a catch. F2 is binary arithmetic. In F2, there are only 2 possible values, 0 and 1. The real world runs on real and complex numbers, where the search space is infinitely larger. Over the real or complex numbers, AlphaTensor could not beat 49. The mathematical community responded fast. Within days, Cowers and Moosbauer took AlphaTensor's ideas and pushed the 5x5 record from 96 down to 95 multiplications. The frontier was moving, but Strassen's 4x4 record over general number systems stood firm. In May 2025, a different DeepMind team tried a radically different approach. Instead of training an AI to play the tensor game directly, they built a system that writes and evolves computer programs that themselves search for tensor decompositions. Here is how AlphaEvolve works. Start with a pool of candidate programs. Each program implements some strategy for searching over tensor decompositions, typically using gradient-based optimization. Now, feed these programs to Gemini, Google's large language model. Gemini reads the code, mutates it, and produces new variants. Run each variant. Score it by how close its output gets to a valid decomposition. Keep the winners. Discard the rest. Repeat. Notice what is happening. AlphaEvolve is not searching for the answer. It is searching for better ways to search for the answer. The LLM does not understand tensor algebra. It understands code. And by evolving code, it explores a space that no human programmer would navigate. The result? AlphaEvolve discovered an algorithm that multiplies 4x4 complex-valued matrices using just 48 scalar multiplications. For the first time in 56 years, Strassen's record was broken. Independent verification came quickly. In June 2025, Dumas, Pernet, and Sedoglavic at the University of Grenoble showed that AlphaEvolve's complex-valued scheme could be projected onto the rational numbers, removing any concern about numerical precision. 48 multiplications verified over the rationales. Let us see the full cascade one more time. Schoolbook, 64. Strassen 1969, 49, AlphaTensor 2022 over F2 only, 47, AlphaEvolve 2025 over the complex numbers, 48. The general field record, unbroken since 1969, had finally fallen. What does saving one multiplication actually mean in practice? By itself, not much, but AlphaEvolve did not stop at the theoretical result. It also optimized how matrix multiplications are actually executed on hardware. By finding smarter ways to tile and partition large matrix operations, AlphaEvolve sped up a critical computation kernel in Gemini's architecture by 23%, reducing Gemini's overall training time by 1%. Across Google's global data centers, it recovered 0.7% of total compute. But let us be precise about what did not change. The asymptotic exponent of matrix multiplication, called omega, describes how the cost scales as matrices grow arbitrarily large. The current best bound, omega less than 2.371339, was set by Allman, Duan, Vasilevska-Williams, and collaborators in 2025 through purely human mathematics. AlphaEvolve's result does not improve omega. It improves the concrete constant for small matrices. Terence Tao, who collaborated with the AlphaEvolve team on a follow-up paper, offered a nuanced perspective. He described AlphaEvolve as an evolutionary system where the stochastic nature of the language model can actually be an advantage. Many hallucinations get pruned out through poor performance, but a few add enough diversity to escape local optima. Tao also noted that AlphaEvolve has not disproved any major open conjecture. This is an important distinction. AlphaEvolve is a powerful search engine, not a mathematician. It cannot prove theorems. It cannot explain why 48 works. It finds candidate constructions in a vast space, and humans or formal verification systems confirm them. The result is real. The understanding is still ours to build. One more caveat. The AlphaEvolve paper is a DeepMind technical report posted to RxAV. As of today, it has not been published in a peer-reviewed journal. The mathematical result itself has been independently verified, but the broader claims about AlphaEvolve's capabilities across other domains await formal scrutiny. Strassen spent years of human thought to save one multiplication. AlphaEvolve ran for hours. The mathematics is the same. The method of discovery is not. Whether that means mathematics is being solved or merely searched is a question we are only beginning to ask.